Starting to record. This is now lecture number 7. First of all, how was the quiz last week, by the way? Everyone?
It was good.
Say it again.
It was easy.
When was the quiz? Was it a week from? Oh, it was last Thursday, right?
You had give us till like the Sunday night to do the quiz.
Right. So what did we do last time? We didn't start chapter 4 yet, did we? Did we
I
finish?
don't think so. We finished up chapter 3.
We finished 3. Okay, so this is lecture number. So this is our 7th lecture then, right? Because we had a quiz last time. So
Yes.
a week ago. Okay, so let's start with regression and correlation. And we will start on slide number 2. Okay, number 2. So we already know that there are 2 types of variables, categorical and quantitative. This was chapter 1, right? We had this done for a while. What we're going to do now is we are going to subdivide those 2 types of variables into 2 further categories. So let's start with categorical. We already know that categorical variables put things into categories that even when you have numbers, you can't really do any math with them. But even amongst categories, there are still 2 different types of variables. There's nominal and there's ordinal. Nominal are categories with literally no order to them whatsoever. For example, as they list there, eye color. They're straight up categories, right? There's no Hello? Okay, so eye color, there's no order to eye color. Blue, brown, hazel. I think that's it. Is there any other kind? I don't even know. But there's no order. It's just categories. Gender, male, female, categories. Race, categories. Marital status, single, married, divorced, etc., categories. What state you live in, categories. There's no order to them. However, sometimes even amongst categories, there is an order. For example, students who get an A or a B or a C or a D or an F, they're categories, but they're ranked. There's a highest and lowest. Social class, upper class, middle class, lower class, military rank, general, colonel, lieutenant colonel. Major? Anyone here in the armed forces? Is it major that's next? Major?
What was the question again?
It wasn't a question. I don't know too much about the armed forces myself. I'm just wondering what the ranks are. I think it's general, colonel, lieutenant colonel. I think major's next. Is that right? I don't know.
After lieutenant colonel?
Yeah.
Colonel.
No. We're going downwards. We're not going up.
Oh, going
General,
down.
colonel, lieutenant colonel.
Major, yeah.
It is major. Okay. So, major, captain, and whatever. So there are categories, but there's an order to them. So that distinguishes the categorical variables, nominal versus ordinal. Quantitative is a little harder to distinguish. You have discrete versus continuous. Discrete means that the values have, and this is very qualitative, this is not very rigorous, but the values have a space in between them. So if I say how many keys do you have, you can have 0 keys, you can have 1 key, you can have 2 keys. You can't have 1.7 keys, right? You can't fit them in between, correct? You can only have 0, 1, 2, etc. Shoe size 7 or 7.5, 8, 8.5, 9, 9.5, right? There are spaces in between them. Interest rate, 7.25, 7.5, etc. These have spaces in between. They are discrete quantitative data. This is as opposed to continuous data. If I say, how high are you? How tall are you? Oh, I'm 5 feet. Well, actually, I'm 5 feet 2 inches. Well, actually, I'm 5 feet 2 inches and a quarter. Well, actually, I'm 5 feet 2 inches and a quarter, 0.1. I mean, you can subdivide those values as close down as you want. Anthony, I have you here late though, but I have you here, but better late than never. So you can subdivide those categories as often as you want. They are continuous, right? They are bunched up. There's no gap in between these possible values. Same thing with weight. I might describe my weight. I'm here too, Weston. I might describe my weight by saying, oh, I'm 180. Oh, I'm 181. Oh, I'm 182 or 180.1. But in reality, even though my approximation might be discrete, the actual value is continuous. Does that make sense? The difference between the actual value versus how we might describe it? Hope you forgive me eating dinner. I teach 6 classes today, and I haven't had a break. So, when you do collect your data, oftentimes you want to analyze it. As we're going to see later in the chapter, we're going to use a spreadsheet to do so. And Microsoft Excel is a great one to do. We're actually going to use something called Crunch It, which I have, which is kind of nice. Your calculator can, of course, do it for you. But the point is that spreadsheets can do a lot of our work for us. They're really, really awesome. And we want to get in the hang of it. Discrete is the one you can group. What do you mean by group? What does group mean? Something about group and my Wi-Fi cut off. I don't remember. Discrete is quantitative data where the numbers have gaps. 1, 2, 3, 4, 5, 1.5, 2.5, 3.5, and so on. Hold on. So categorical, there are categories, and those categories are ordinal, where there's an order to the categories, or nominal, where there's not. And then there's quantitative data, numbers that you can do math, where they're either discrete, the number of values are separated, or it's continuous, the numbers can take on any value. So if you ask the following questions of a group of students, what's your height in inches? Are you male or female? Would you label yourself as liberal, moderate, or conservative? How many children would you like to have? Let's list those in terms of which category are they in. Are they ordinal, nominal, discrete, or continuous? So let's do the first one. What is your height in inches? Ordinal, nominal, discrete, or continuous? Continuous, good. Male or female? Nominal, no order. Liberal, moderate, or conservative? With no bias. There's no best. It's nominal, right? Again, no order. How many children would you like to have? That's discrete, right? Last time I checked, you can have 1.739246 and so on kids. So let's go to the next slide. This is just a picture of a Excel spreadsheet where you asked a bunch of questions of your students and they answered them all. 71 inches, male, undeclared political orientation, 0 kids, and so on. Nothing special about that. So up until now, we have focused our attention on one variable at a time. You have one variable. What does it mean? What's its median? What's standard deviation? The quartiles. Is it normal? Less than this? Greater than this? All things about one variable. Symmetric, right symmetric, left symmetric, skewed, who knows? But what we want to do now is we want to look at 2 different variables and compare them. Does this explain this? Is there a connection between this and this? As this one goes up, does this one also go up? Maybe it goes down. Does it go up in a predictable way? If you change this a little bit, can I tell you how you're going to change that? We want to compare 2 different distributions. So on slide 6, we have our first slide dealing with 2 different quantities at the same time. The first thing to understand is that what we do in this chapter, in chapter 5, is specifically for quantitative variables. Whether it's discrete or continuous, I don't care. But what we're going to do here applies specifically to quantitative, not categorical. You cannot use any of the math that we are going to construct for categorical data. This is only for quantitative. And what you're going to have is you're going to have 2 different things. You're going to have what we call the explanatory variable, and you're going to have the response variable. And the goal is going to be, does this variable explain this variable? So could someone give me an example out there in the world of 2 quantitative variables where one might help explain why the other one is what it is? So we have 2 good ones here. Height and basket scored. I assume we're talking about basketball here. The taller a person is, maybe that has an indication of how well they would perform playing basketball. Grades and GPA. Well, grades and GPA is really the same thing. But exam grades and GPA. Okay, so better exam scores, higher GPA. Sugar consumption and body weight. I'm not sure if you're implying anything there, but certainly sugar consumption and body weight. I mean, they're all out there. They're hours of sleep and how many times you yawn the next day. Hours studied and GPA. There's so many situations. Now, when you say that hours of sleep is used to explain how many times you yawn, or how many times you yawn is used to explain how many hours of sleep? So while sometimes it can go either way, in some situations it's very clearly this one is explaining that one. The one that's doing the explaining, that's going to be your explanatory variable, and that's going to be on the x-axis. The one that is responding to that, that's going to be on your y-axis. We call that the response variable. So if you look on slide 6, we have the explanatory variable, the x variable, independent variable, the predictor variable, and then we have the y, the response. The y variable, or the dependent variable, depends on x. X, make it whatever you want, but y depends upon x. Does that make sense? Any questions so far on these concepts? No math yet, just concepts. Seems reasonable? So let's look now at slide number 7, some examples. This is not, I mean, these are just possibilities. So if we look at the first line for college GPA, we have different things that might predict your college GPA. Amongst them, your high school SAT scores and your high school GPA. Both of those might be a good predictor of college GPA. Price of a home. What are some things that might go into it? Square footage, the lot size, number of baths, the age, the location, right? We have all these situations, right? All these things are good predictors of the response. Now, when it comes time to actually do the math, the more predictors that you have, the more complicated the math is. Because if you want to predict why something is the way it is, and you have multiple things that are doing predicting, you can get really convoluted. So we try to do one at a time. However, in this class, we're not going to be studying how you can take a number of predictive variables and create one at a time. We're just only going to do examples of one at a time because it's a lot easier. So even though there's lots of reasons why it might be what it is, nevertheless, we're going to focus on one at a time, one predictor, one response. We call that simple. Well, I don't want to use that term yet, but we'll get to it. So now let's look at slide number 8. So slide number 8 talks about a scatter plot. A scatter plot is a graph which displays the relationship specifically between two quantitative variables: explanatory, response. If you look at, and a scatter plot should always be done first. Before you jump into your math and decide to calculate this, to calculate that, etc., the first thing you should always do is do the math first. So if we look at slide number 9, we have an example of a scatter plot. This question is a study done of whether or not there's a relationship. No problem, John, good to have you. So this problem is a study of whether or not there is a relationship between the temperature at a Yankees game and the amount of beer sales at that same Yankees game. Someone hypothesizes and says, you know what? I think that as the temperature goes up, the beer sales will also go up. So what do you do to test that? You go out and you keep track of a certain number of games where you can record both the temperature and you can record the number of sales. And you see that when we do that, this particular example, the person went out and did it for 10 different games. On the x-axis, you have the temperature because it's the explanatory variable. On the y-axis, you have the response variable, and we have the scatter plot. Now, from the looks of this scatter plot, does there seem to be a relationship between temperature and beer sales? What type of relationship does there look like there's going to be here? If you haven't learned this yet, that's great. What general shape does this graph appear to be?
Linear.
It looks linear, right? It looks fairly linear. Now, we will learn the mathematics in this chapter to determine how linear it actually is. But it certainly looks like I can draw a line through it that will pretty closely approximate the points, correct? So when we draw scatter plots, we are looking for 4 things. If you look at the next slide, slide 10, there's 4 things that we are looking for. What are those 4 things? 1, the form. Is it linear or is it nonlinear? In our example, it certainly looks linear, does it not? I'm not perfect, of course. It's not all going to form on one line. You can't expect reality to mirror perfection, right? I mean, different people attend different games, and maybe they're thirsty or not thirsty. You can't assume it's going to be a perfect relationship. We're looking for the overall relationship. Does it look linear or not? 1. 2, whether it's linear or not, does it seem to go up? So that as the explanatory variable increases, the response variable increases, or does it seem to go down? Explanatory increases, response goes down. In our case, would it be positive or would it be negative? In the slide in the previous page. It certainly looks positive, right?
Positive correlation. Yeah.
Certainly looks that way, right? The next one's a little tougher to do by eye. We'll have a mathematical way of doing it. But the next one's called the strength. How strong of a linear relationship is there? We're essentially going to have 4 or 5 levels. Perfectly linear. They all fall exactly on a line. Strong. Not on a line perfectly, but pretty close. Moderate. Weak. Or just straight up, I don't even see a line, nonlinear. So it's going to be perfect, strong, moderate, weak, or essentially non-existent. 5 levels of strength. And we're going to have mathematical ways of predicting which one it is. And then someone said, oh, so you're saying, oh, I didn't even ask that. But okay, so you're saying that ours is moderate. You know what? We're actually going to come back to this later, even though it's not in the PowerPoint, but we'll come back to it later after we learn how to mathematize strength, and we'll check whether or not it's right. The 5 types of strength: perfect, strong, moderate, weak, or non-existent.
Kristen, what are we talking about?
Okay?
What do you know about
I don't see who's not on mute. But, okay, anyways, back to the regularly scheduled broadcast. Okay, so let's, actually, you know what? We can even do it now before I forget. So let me show you how to do this. We're gonna, how many data points were there for the beer game, for the, where is it? Where is it? It was, here we go. So I'm gonna share my screen here. And I'm gonna load up. I'm gonna, oh, there it is, Crunch It, okay. So I'm gonna load up Crunch It. Let's ignore this. We don't need this right now. Okay. Okay, and we're gonna come up with a file new. So you don't have access to this program, but that's okay because it's still gonna demonstrate what we need to demonstrate. So let's move this over. And then let's do this. Okay, so my explanatory variable, 80, 68, 78, 79, 87, 74, 86, 92, 77, 84. And then my response is 2533, 1439, 13,829, 21,286, 30,985, 17187, 3240, 37,596, 9610, and 28,742. So what I'm going to have this cruncher do, go to graphics, go to scatter plot, and it's going to make a scatter plot. So do we agree that what we have here is basically the same one that was in the PowerPoint?
Yes.
Certainly seems very close, right? Okay. So let's go back to sharing the screen. So what I'm going to do now is something that we're going to learn about. I'm going to calculate the correlation. So 0.9538. Whatever that means, that is the correlation between these two variables. So keep that number in mind so that later, when we learn how to I don't even know what the word is. When we learn how to associate mathematics with correlation and strength, we will have an answer to our question of whether this is strong, moderate, weak, non-existent, or perfect. It's certainly not non-existent because we notice it, and it's certainly not perfect because they're not all on one line. Question is it strong? Is it moderate? Is it weak? We'll get to it. Perfect, strong, moderate, weak, and non-existent. Okay. So let's scroll down now to slide number 11. All right, this gives us some examples of the various forms. First one on top left is linear. Not only is it linear, but what would be the strength of that one, would you say?
Strong.
It's strong, but how strong?
Perfect.
It's perfect. It falls on a line. So it is perfectly linear. It's more than strong. It's perfectly linear. How about the one to the right of that? What would you say there?
Strong.
Seems very strong, right? Very tight around the line. How about the next one?
Moderate.
Okay, I would think so. The one at the bottom left?
Weak.
Weak? I mean,
Or the last one.
Non-existent.
Non-existent.
it might even be non-existent, right? It's I mean, maybe I see a general upward trend, but it certainly seems like it's just a blob of points. But the math would tell me, so this PowerPoint is claiming that it's linear. I don't see it as being linear. I just see a blob, but as we're going to see, nothing beats the math. How about the next one? Linear?
Curved.
This is a curve, right? This is certainly not a linear function. I would still say it's whatever relationship it is, it seems pretty strong, but it's certainly not linear. And how about the one at the bottom right?
Curved, moderate, weak.
Yeah, also seems pretty curved, moderately strong, hard to tell without having a scale, but certainly not linear. And in terms of positive or negative, if you look at the next slide, 12, the first one is certainly negative, then positive, then negative, then if it exists at all, positive, because it does seem to trend upwards a little bit. Next one is both, down, then up. And the one after that is just down. So usually we really don't care if it's not linear, but we can still answer the question of how strong it is, whether it's linear or not. Does that make sense so far?
Yes.
Could the last one technically be both?
Well, do you see it going up?
Sort of.
Well, it certainly seems like it's starting to maybe start trending upwards, but I don't think it really does yet. It could be like an exponential, which asymptotically decreases. I don't really see the increase, but if you thought there was, I would certainly recommend taking more data in that area to see what happens, right? As a statistician. Would you agree?
I'd agree.
Yeah, kind of hard to see, but if you're not sure, take a little more data in that area and see what happens. Anyway, then we have relative strength. So let's see if we were right. Perfect, very strong, as opposed to strong, weak, very strong, strong. Again, very strong and strong, we're not going to distinguish between them. We are going to have 5 levels: perfect, strong, moderate, weak, non-existent, and we will have a mathematical way of computing it, as we're going to see. And if we look at slide 14, it's just always be on the lookout for unusual observations or outliers, both for 2 reasons. 1, it could be a mistake, or 2, it could be real, but there could be a reason why it's there, and we might want to remove it from the overall trend. Or 3, maybe we can remove it from the overall trend and we need to keep it. That's not a mathematical decision. That's a practical case-by-case scenario decision. Okay? Now look at slide 15. Don't look at 16, just 15. And tell me which of those two scatter plots would you say is stronger? The top one or the bottom one? So I see some answers here. 2 people say bottom, a lot of bottoms. Okay, 1, 2, 3, 4, 5 bottoms. Now everyone's saying bottom. Anyone gonna say top? Bottom, 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 bottom. Lots of bottoms. And then someone finally says, aren't they the same because of the scale of the graph? This is the same data. This is exactly the same data, which means, sorry, bruh. Okay, it's the same data, which means it's hard to trust your eyes when it comes to this. Because you good, you got us, SMH, shake my head. That's right. So, what's wow? What's wow? We got juked. No, that's not, I haven't heard that one. Sorry, bro. Bro, I've heard, but juked? I don't know what that means. Poggers, yeah. I know poggers, that's right. Anywho, didn't mean to hurt you, but it's your own fault. Anyway, so what do? We come up with a mathematical measure of strength. And that is on slide number 16. So, this formula looks very complicated. And it is, we're not going to use it. However, when you look at this formula, you should see a typo. Does anyone see a typo in this formula? Not 1 to 10. We're going to see exactly the scale, but it's not 1 to 10. But what's the typo in the formula? Come on. It's obvious. Look closely. When you see it, you'll see it. Whoever put this down made a mistake.
Under the first parenthesis, there it's divided by s of y when it's supposed to be s of x.
Exactly. So don't just copy that because whoever wrote this PowerPoint made a mistake. But x's go with x's, y's go with y's. So what do? We do the first x data point, x1, minus the average of the x's, minus x bar. The shorter form is great, right? The shorter form is fine, but it's the upper form that was bad. And then we divide that by sy. Actually, you know what that is? X1 minus x bar over sy. That is the z-score for x, isn't it? Subtract the mean and divide by the standard deviation, right? So we multiply the z-score for x, the first x, times the z-score for the first y. Same for the second, same for the third, same for the fourth, same for the fifth, all the way to the nth one. Add them all together, divide by n minus 1, and this gives us r. This gives us the correlation between them. The correlation measures how strongly the linear relationship is. This is very important. No, you don't add the z-scores. You multiply the first x z-score by the first y z-score, the second x z-score by the second y z-score, the third pair, the fourth pair, the fifth pair, all the way to the last pair, and then we add them all together and divide by n minus 1. Okay? Now, of course, your computer, your calculator will do that for you. You don't got to do it by hand. Okay? But you should just know what's being done. So this gives us a correlation. Now, the correlation measures the linear association. This is very important. If there is a association that's not linear, this math will give you nonsense. It does not tell you whether they're associated. It tells you whether they are linearly associated. So if there's some other kind of association, that's great. And sometimes it's important, but you're not going to get that from this math. This math is about the linear association and only the linear association. So how do we, in our example that I did on Crunch It, what do we get? 0.95 something. So the question is, what does that 0.95 something mean? So let's quickly answer it by going to slide 18, because I know you're all interested in knowing what is the scale. Look at slide 18 for a second. So R values. If the absolute value of the R value, because remember, it could be negative, positive going up, negative going down. If the absolute value of the R value is 1, that is a perfectly linear relationship. If it's 0, then there is no relationship. But we have a general rule of thumb. If R, or at least its absolute value, is between 0 and 0.1, then essentially there's no linear association whatsoever. It's just not there. Is that table universal for all data? What do you mean by that? Yes, you can reference this table for this class. That's correct. This table is the general rules that we will be using for this class. However, if you get a value in real life of like 0.500001, you're not going to say, oh, that's moderate, and then 0.499999 is weak when they're so close to each other. These are arbitrary cutoffs. So if you're really close to one edge, in this class, this is the table that we're going to use, but in real life, just be aware, these are arbitrary cutoffs. So you'll notice that half of the R values from negative 0.5 to 0.5 correspond to either no relationship or a weak relationship. 0.5 to 0.8, that's 30% of them, that's moderate. At a 0.8 greater than 1 is considered strong. If it's actually 1, then it's perfect. So if we go back to our example, we got an R value of 0.9538. And as such, a 0.9538 would correspond to what? What will we call that? What is the strength of 0.9538? Anyone?
Or strong.
Strong. Maybe even very strong. Okay. So let's go back one slide and now give some properties of the correlation. So R is a measure of the correlation, measure of the linear association, and there's 4 properties of R. 1, R will always be between -1 and 1. Okay, R can never, if you get a mathematics that is outside of -1 and 1, you made a mistake. R must be between -1 and 1. There are no units for R. Okay, it is a unitless quantity. R has no units whatsoever. The sign of R, if R is positive, it tells you that it's going up. And if R is negative, it tells you that it's going down. The value gives you the strength, as we saw on the next slide. So back to the next slide again, we have our 5 cases: no association, weak association, moderate, strong, and perfect. And they are all determined by R. So you don't have to worry anymore about what your eyes see. You just plug the values into the calculator or to the computer, and it pops out the answer. Are there any questions on that? So if you look at slide 19, here we have the top two are both perfectly linear. In the first case, R is 1. The second case, R is -1. After that, we have a blob of points. There's no general trend, even a weak one. R is approximately 0. And the correlation between X and Y is the same as the correlation between Y and X, even though you have the explanatory variable and the response variable. If you were to flip them, the correlation will be exactly the same. Okay, so correlation does not depend on which one is your explanatory and which one is your response. Are there any questions so far? All right, so please turn to slide number 20. And we will do an example. And we are going to carry this example to the rest of this PowerPoint. So this example we're going to use quite often. So I'm going to go, well, I'll get to it in a minute. Okay. So the following data, the following tables display sample data for 5 cars of comparable type. You're in the market to buy a car. The general trend is the more miles that the car has on it, the lower the selling price is going to be. So as miles goes up, selling price goes down. Does that seem to be the true pattern from this table, from this data? That as mileage goes up, selling price goes down. It certainly seems that way, right? In fact, you can see 35.7. We see a general negative trend, okay? Which is good, because a negative trend is exactly what we would expect. If we get something that's not what we expect, that's when we start to question what we have. So let's look what they have there. First, on the top left, or the middle left, whatever, they focused only on the X variable, and they calculated its X bar, which is its mean, and its S sub X, which is its standard deviation. And I'll trust their math, that's what they got. Then they did the same thing for Y. They did its average, 7.84, and its standard deviation, 0.82644. Again, I will trust that. Then they calculated R. Now they calculated R in a different way. If you look at slide 17, a couple slides ago, you'll see a couple other formulas for R that are mathematically equivalent to the one that was given. We're not going to need them, which is why I didn't really focus on them. But there are 2 other formulas they can use. So in this slide, where were you, slide 20, they happen to use a different one. And they got a value of negative 0.96. So what we're going to do is we're going to verify that. I'm going to go back to Crunch It. And I'm going to get a new file. My X values are 35, 22, 32, 18, and 25. With my response variables as 7, 8.5, 7.2, 8.9, and 7.6. Statistics, graphs. So let's make a scatter plot. Let's see what this thing looks like. Is that roughly what was given in the book?
Yes.
Seems to be exactly the same. So the correlation, negative 0.9599, and that seems to be in line with what they got here. Agreed? Yes, no, maybe so?
Yes.
I have a question.
Yes.
Are we always going around to 2 decimal points?
Yeah, unless they specifically say otherwise. If they say round to 4, round to 5, for whatever problem you're doing, then follow the instructions. But in general, 2 is okay.
Thank you.
Okay. So we have the negative 9.96. What does that tell me about the graph, or about the data more specifically? It's strong. Don't worry about what they divided by. They used a different formula than we did. So don't worry about it, but it is strong. 0.96 is actually very strong. Even though this one's a little off, it still was very strong. Okay, so that takes us to the end of slide 20. Any questions so far? All right, well, before we begin 21, which is chapter 5, let's take a 5-minute break. So we'll come back at 7:27 on my computer, and we'll move on to the second half, which is chapter 5. All right, are we all back?
Yes.
Okay, I hope so. So it is now, so it's 7:28. We're still on the same lecture. And now we're going to move on to chapter 5, which is very close to chapter 4. They're very much connected. 4 is on correlation, and 5 is on regression. They're connected, they're different. But before you do anything, you want to make sure that what you're dealing with is a line, which means the first step is make your scatter plot and compute your correlation. And once you've done that, you should know whether or not you have a linear relationship and how strong it is. Okay? Assuming that it's a strong or moderate linear relationship, you now are going to go into finding the best fit line for that data point. And we're going to put best fit line in quotation marks, because at this point, we don't really know what it means to best fit the data. If I have the following data points, does this data look linear? What slide are we on? We are on slide 21. So does this data look linear? No, it doesn't? Okay, well, how about now? Does it look linear now? Okay, amazing how adding 1 point can change a graph from nonlinear to linear. But just so you know, we're going to learn a term later called an influential point, that if you have a point or two that drastically changes the nature of the relationship, we call it influential. But if you believe that it's linear, and let's say for the sake of this example that it is, we like to come up with a line that best fits the data. And would something like that seem reasonable as a best fit of the data? I'm not saying that is the best fit, but does it seem like that sort of encapsulates the overall pattern of the relationship between them? It seems pretty good, right? But if someone else made another line that was like this, let's see if I can use a different color. If someone else did this, oh, that was good. Let's say someone else did that. Or that. or this. I mean, any one of these, excuse me, any one of these can reasonably be considered to be the best fit line, correct? The line that best fits the data. So the question is, how do we find the one that actually does best fit the data, and how do we know that we found it? So this is what regression is. Regression is the mathematical way of determining the best fit line, okay? Unfortunately, to actually compute the best fit line requires not just calculus, but multivariable calculus, which is not a prerequisite for this class. Does anyone here, so looks like a bunch of dots. No, I mean, it is a bunch of dots. It's data points. And the question is, do those data points give us a linear relationship? Do we expect that if I would compute thousands, millions of data points, that I would have roughly a linear relationship? So has anyone here taken multivariable calculus? Has anyone gotten that far in their studies? Ooh, no. Okay, no, that's okay. Ooh, I'm scared. Okay. Multivariable calculus is actually easier than single variable calculus once you already know single variable calculus. I'm not saying it's easier overall, but the learning curve is that to learn calculus 1 is very tough. But once you know calculus 1, learning calculus 2 and calculus 3 is actually easier, in my opinion, but what do I know? Anyways, we don't have multivariable calculus here, so I'm taking Calc 1 right now if that helps. It doesn't, but thank you for contributing. So let's do the following. I'll just show you. I am going to load up, that's my emails. You don't need any of that. Where is Crunch It? Right here. Okay. So we have here our data for this problem. We've already computed the correlation. So we know that it is very strongly linear. So I'm going to go here to graphics, no, to statistics, to regression, simple linear, and I'm going to have it make a fitted plot. So when it does that, this is in its, well, I don't want to say in its opinion, this is the computed best fit line for this data by whatever standard we're going to use. This is the best fit line. Out of all the infinitely many lines that we can possibly come up with, this is the best of them all. And the question is why? So let's go back now and look at slide number 21. Calc 2 is harder than Calc 1. Well, yeah, maybe. Maybe. I can't argue with you on that one. But Calc 3 is easier than Calc 2. That one I can say. Anyway, so regression analysis, the study of the relationship between one or more explanatory variables and a single response variable. In this class, the explanatory variable will always be one. We call that simple linear regression. One explanatory variable, one response variable, as opposed to multiple explanatories and one response. It's always one-to-one. And simple linear regression is a statistical procedure that we're going to use to come up with the equation of the best fit line. Now, what is the form of a line? It's y equals mx plus b, right? That's what we learn about in high school, y equals mx plus b. For whatever reason, in statistics, we don't use mx plus b, we use a plus bx. It's just a rearrangement and labeling them with different letters. The number next to the x is the slope, and the number by itself is the y-intercept. Correct? It's no different. So we are looking for a and b. We want to know what is the slope, and we want to know what is the y-intercept. Once we have that, we have the line. So without going into any of the details, because I just can't, without multivariable calculus, look at slide number 22. What is the goal? So the goal is as follows. When I have my belief in what the best fit line is. What makes it the best fit line? It's the following. For this x value right here, this guy here is my observed value. That's what I actually got, right? For this x value, this is my y. That's what I actually got. But if this line is correct, then that should have been what I did get. We call this the expected or predicted value. X value with the corresponding y, that's my data points. But this guy here, that's what I should have gotten. We call that y hat. We use the hat symbol for the predicted value from the best fit line. So the residual for this point is the difference between what I actually got and what the line tells me that I should get. The residual is y minus y hat. It's the difference between what I actually got and what I should got. Okay? What we're going to do is we're going to calculate the residual. And in fact, there's another slide here which does a good picture of this, slide 23. So if you look at slide 23, it's a better picture of the situation that we're dealing with. So take a look at that. Okay, so we see that for the x value of 18, what is the y value that we got? 8.9. If the line truly was the correct linear relationship, then what do we think we should have gotten for an x value of 18? About 8.6, right? So the residual in this case is going to be 0.3. The residual is going to be 0.3, what we got minus what we should have gotten. And what we can do is we can calculate the residual for every one of our data points. Every one of our data points will give us a residual. Some positives, they're above the line. Some negative, they're beneath the line. Now, if I add up the residuals, I'm going to get 0 because they're going to cancel, positives and negatives. However, if I square the residuals and add those, so go back to the previous slide, slide 22. If you take the square of the residuals and you add them, the goal is to make that as small as possible. So in theory, what I'm doing is I'm going to test every single possible line and see out of all of the infinitely many lines that are out there, which of them give me the smallest sum for the squares of the residuals. Whatever line that is, that's going to be my best fit line. Say again? No? Okay. That's going to be my best fit line. I square the residuals, I add them together, and I pick the line that makes that as small as possible. Now, I don't know about you, but I don't have the time to test every one of the infinitely many possible lines to see which one will give me the smallest value for the sum of the squares of the residuals. This is where multivariable calculus comes in. It does it for me. It's about 5 lines of work, and then I have the answer. I'm not saying it's easy to learn multivariable calculus, but once you know it, this particular problem is not very difficult. The answer is very quick, and it actually is on the next slide, slide 24. The equation of the best fit line is given by y hat equals a plus bx. Remember, b is a slope and a is the y-intercept. So according to this slide, and again, we're not deriving these formulas, but according to the slide, what is b? What is the slope? The best line equals the smallest sum of the squared residuals. In a sense, the best line is the one that will give you the smallest sum of the squared residuals. We call it the least squares regression line. It's the one that will give you the sum of the squares as small as possible. Out of all the infinitely many lines, because remember, there's infinitely many slopes and infinitely many y-intercepts. So out of all the infinitely many lines, it's the one that makes that as small as possible. And after you finish all of your calculus, multivariable calculus, you get the final result that the slope is r times sy over sx. What is r again? What's the formula for r? Not formula, but what does r stand for? What does r stand for again?
Correlation.
Correlation. What is s sub y? What does s sub y stand for?
Standard deviation.
Of what variable?
Y.
Of the y variable. And what is s sub x?
The x variable.
The standard deviation of the x variable. So r sy over sx gives us a slope. And once you have the slope, I can use that to find the y-intercept. Because what's the formula for the y-intercept? It's y bar minus bx bar, correct? I mean, that's what's given there. I mean, you can't really argue with it because we didn't see it derived, but that is certainly what's given there in the page, right? That the y-intercept is y bar minus bx bar, right? So once you have b from the previous equation, you plug it in. What is x bar and y bar referring to? What are x bar and y bar?
Average.
Which average? Be more specific.
The x
Which
average.
mean, huh?
Like the x average.
Well, which one is the x average?
The x with the bar.
Okay, and what's y bar referring to?
The y average.
Okay, so once you have your x bar, y bar, and your b, you can find the y-intercept. So if you look on the next slide, slide 25, we see that they did that for us. And they got, for our example, they got y hat equals 10.82 minus 0.113x. So let's go back to crunch it and see if they give us the same thing. Statistics, regression, simple linear, numerical results, calculate, and it gives me that variable 2, which is my y, equals 10.82 minus 0.1130 times variable 1, which is my x. So 10.82 minus 0.1130x. 10.82 minus 0.1130x. There we go. So isn't it nice to have a calculator that can do that all for me? So that I don't gotta do it myself. That's really awesome, huh? I know, you're all thinking the same thing even though you're not saying it. Okay, so you can skip slide 26, don't need it. Let's go to slide number 27. So slide number 27. Slide number 27 is what's called the coefficient of determination. The coefficient of determination is mathematically related to R. In fact, from a mathematical standpoint, it's very straightforward. You just take R and you square it, right? So if R is 0.96 or negative 0.96, like the last example, R squared is about 0.92. It's just you square 0.96, you get 0.92. The question is, what is R squared telling us? So let me ask you the following question. Suppose I was to measure the heights of children as a function of how old they were. So my X value is their age from, let's say, just born to, let's say, 2 years old. And my Y value is their heights. Are all the Y values going to be, if I look at 1,000 babies, are all the Y values going to be the same? Yes, no, maybe so?
No.
No. Why wouldn't they all be the same? Give me 2 reasons why their heights would not all be the same. Give me 2 reasons why the heights of all these babies would not be the same? Forget about math. Just give me 2 reasons. Different babies, different heights. Man, I know that they would have different heights. I'm asking why they would have different heights. Why are all the babies not going to be the same height? I want 2 different reasons. Let's assume they're all normal babies.
Their parents' height?
How, say it again?
Their parents' height?
Okay, so one reason is genetics, right? Born prematurely, dwarfism. These are all reasons why babies are going to have different heights, correct? Right?
Yes.
Genetics, nutrition, how well the mother took care of herself during pregnancy, whether there's just a genetic disorder, dwarfism, or maybe gigantism, or whatever the opposite is. These are all perfectly valid reasons why their heights are going to be different. But you're all missing the most obvious reason why babies from 0 to 2 years old are not all going to be the same height. Why would a group of babies from 0 to 2 not all be the same height?
The 2-year-olds would be bigger
Why?
because they're older.
Because they're older, right? The most obvious reason why they're not all going to be the same height is because they're not all the same age. My X values are different. If my X values are different, it seems very reasonable that my Y values are going to be different. Correct? Yes, no?
That makes sense. Yeah.
That makes sense, right? If their X values are different, their Y values are going to be different. So the question is, of all the reason why their Y values are different, how much of that can be attributed to different X values? And how much of that can be attributed to all the other stuff that we're not considering, like genetics and genetic disorders and all the other considerations? So this is what the coefficient of determination gives us. If you look on slide 27, R squared, if you square your R value, tells you 1% of the variation in your Y value comes strictly from the variation in the X value. So in our example, we had a negative 0.96 correlation, which means our coefficient of determination is 0.92. 92% of the reason why the selling prices are different is because the mileage is different. The other 8% comes from other factors like age of car, like color of car, how many accidents the car has been in, all the other considerations that we're not focusing our attention on. That's the other 8%. But R squared of 92% tells us 92% of the reason why the Y values are different is simply because the X values are different. Don't read into it any more than that. But the other 8%, that is a different story. That is all the other stuff that we're not considering. So if I have an R squared value of 100%, that means I don't got to look further. All of the reason why Y is different is because X is different, and it's going to be perfectly linear. There's no randomness. There's no variation. There's no other things to consider. But in general, there will be. Does that make sense? I hope so. No one's saying anything otherwise, so I hope it makes sense. Okay? Now, why do we care about the best fit line? Let's turn to slide number 29. You look at your 5 data points. You came up with the scatter plot. You decided that it's linear. You came up with your equation of the best fit line. And then you come across a new car that you haven't seen before that has 28,000 miles on it. And you say, oh, I kind of like this car. I wonder what its selling price should be. Well, we're going to use the best fit line to predict the values for any other X that we might have. So what do? I just plug in the X value. When I plug in 28, not 28,000 because the units are thousands of miles, but when I plug in 28 into my equation, I get 7.66. 7.66 what? $1,000. So if my best fit line is correct, this is my prediction on what the selling price should be. And if X was 20,000 miles, then this now is my prediction on what the selling price should be. So we take our data, we get the best fit line, and then we use the best fit line to predict what our Y should be for different values of X. Does that make sense? I hope so. So let's now turn to the next slide. It's a different example. This is slide number 30. This is family vehicle data. There is 1, 2, 3, 4, 5 data points. There's a typo on the top. The number of children and the number of cars are slightly offset from each other. So the bottom line should be shifted a little to the left, which means what is our first data point? 4 children, how many cars? First data point, 4 children, how many cars? 3. Next data point, 1 child, how many cars?
1.
1, 5, 3, 2, 2, 3, 2. The data is plotted. So they took the data for us. They put it into a calculator of some kind. And if you look at the top of the graph, it says cars equal 0.7 plus 0.5 children. So in other words, my A is 0.7, my B is 0.5. That's what the math gave us. Okay? Agreed? You're all with me so far? So if I have 2 children, what does the line predict should be the number of cars? Well, you take 2 and you plug it into your formula, and out pops the answer, which is 1.7. Can I have 1.7 cars? No, of course. We're talking about averages here. Right? You can't have exactly 1.7 cars. It makes no sense. But on the average of all the families with 2 children, on the average, they would have 1.7 cars per family. And if they had 4 children, they'd have 2.7 cars per family, and so on. And so on. Okay? So the question is, what is a physical interpretation of the slope? And what is a physical interpretation of the y-intercept? If I have a slope in this case of 0.5, 0.5 what? What does that mean, 0.5? What is the physical interpretation of 0.5? Point 0.5 what? How do we interpret the slope? 0.5 what? Nobody knows? Or nobody's listening? Or nobody cares? Could really be any one of the 3. I accept that as a possibility. So slope is rise over run. Okay? I'm not sure it's totally fine. Slope is rise over run. That means I go up 0.5 and over 1. In other words, for every 1 increase this way, I go up 0.5 that way. So if I have 1 extra child, that's the rate of change. If I have 1 extra child, on the average, I'm going to have 0.5 extra cars. The number of cars goes up by 0.5 for every 1 child that I have. You move this way 1, slope 0.5, 0.5 over 1. Or for every 2 children, I go up 1 car, if you prefer to have whole numbers. That is the interpretation of the slope. What's the y-intercept? It's when the x value is 0. So this tells me that on average, families with no children have approximately 0.7 cars. Right? When the number of children is 0, 0.5 times 0 plus 0.7, no children, 0.7 cars on average. That is what it means. Okay? So unless there's any other questions, this is a good place to stop because the next portion will take more than 15 minutes and I don't want to do it in 2 different stages. So unless there is any question, we can call it here. So yeah, the R squared. the y values in any collection of data are not all the same. The reason why the y values are not all the same is twofold. One, because the x values are not all the same. But even if the x values were the same, I can't expect to have the same y values. That's not how life works. There's always randomness, things that I can't control, things that I'm not considering. R squared, in our example was 92%. R squared is the percent of the variation in your y values that can be explained by the variation in the x values. So if I get 92% as my R squared, that means 92% of the reason why the y values are different is because the x values are different. The other 8% are things that I'm not considering, like genetics, nutrition, nature versus nurture, all the other things that might play a role. I'm not considering them in this study. So the R squared is the percent of the reason the percent of the reason why your y values differ due to the x values being different. Does that make sense or more sense? I hope so. I've been teaching straight for like 12 hours. So my mind is fried at this point. But hopefully that makes sense. If you guys have any further questions, I'll stick around for a few minutes. Otherwise, I will see you guys on Tuesday. The homeworks for 3 and 4 are up. And you should be able to do everything because we finished 3 and 4. So have a good night, everyone. I'll see you guys soon. You're welcome. You're welcome. Ditch tutoring. She pays well. What can I do? Can't really pass up $80 an hour. You too, Rihanna. Have a good night. Yes, that's correct. That's exactly it. I'm going to stop recording.